Welcome to this series of videos on trigonometry. These are meant to supplement part 3 of my book, Pre-Calculus Made Difficult. So let's jump right in. This strange word, trigonometry, what does it mean? Well, literally, if we go back to the Greek roots of this word, it means something like triangle measurement. So you might ask, what's so special about triangles that we want to devote an entire subject to their measurements? Well, triangles are special because they are the building blocks of all polygons, where a polygon is just any figure made entirely of straight lines. That is, no curves are involved. Triangles, I said, are the building blocks of polygons because given any polygon, we can simply triangulate it, which means draw lines connecting its vertices until we have chopped up the polygon into a collection of triangles, like so, or like this, or like so. Given any individual polygon, there may be many ways to triangulate it, but the important thing is that it can always be done in at least one way. And if we are interested in some particular polygon, something having to do with the measurements of that polygon, its side lengths or angles, if we can triangulate the polygon, then we've simplified our questions considerably, because instead of having to worry about some complicated looking figure, we break everything down into questions about very simple figures, namely triangles, which is why we want to know all about triangles. Because if we know all about triangles, then we know all about all polygons, which is a vast family of shapes. It covers everything that does not involve curves. Once we bring curves into the picture, then we generally need calculus. But so long as we're dealing with straight figures, we're working with polygons, and therefore everything reduces down to trigonometry. This is why we have a subject called trigonometry and not a subject called octagonometry or pentagonometry. A figure like this one, which has 6 sides and is therefore a hexagon, doesn't require special knowledge of something called hexagonometry to study it. No, we just crack it into triangles and use trigonometry to get whatever information we need. But as we'll see, the study of triangles will eventually lead us not just to polygons, but in a very interesting way, it will lead us to circles. And that's where the subject of trigonometry begins to transcend its roots in triangles and take on a much more interesting significance. But we'll get to that later. In the early chapters, we really are just talking about triangles. So in particular, in chapter 8 of the book, we need to review some very basic ideas about triangles, almost all of which you will have encountered earlier in your life, in earlier courses. But if you are like most people, you will know a lot of these things only as facts. You may not actually understand why they are true. And the goal in this chapter is not just to review the facts, but to really impress upon you why these various things are true about triangles. Because to understand trigonometry, to understand any mathematical subject, it is vital that you understand why things work the way they do. Mathematics is ultimately about understanding logical arguments, following trains of thought, creating such trains of thought on your own. Yes, these involve calculations, but the calculations are not the thing in and of itself. It's the logical interconnections that make the subject live and that make the subject interesting. And the more you understand, the less there is to memorize. But I will get down from the soapbox and instead give you an example of what I am talking about. Triangle basics. What's the most basic fact about triangles that everybody knows? And I don't mean that they have 3 sides. That's just part of the definition. I mean the most basic, non-obvious fact. The most basic theorem, the first thing that is maybe surprising about them, even if it no longer feels like a surprise to you because it's so familiar. And I'm looking for something that is true about every triangle that has ever existed, every triangle that will ever exist. What is something about every triangle that is true and that is not just part of the definition of the triangle? Well, the answer has probably already occurred to you. Namely, in any triangle whatsoever, the sum of the 3 angles is 180 degrees. Now everybody knows that fact, but see if you can recapture what a remarkable statement that is before it was dulled by familiarity. There are infinitely many triangles out there. And this is telling you that in any one of them that you pick, in all such triangles, the angles always add up to the same thing, namely 180 degrees. You might be tempted to think, well, if I work really hard, maybe I can come up with a triangle where that doesn't happen. But you can't. It always happens. It's a universal statement. And it is precisely that universality that is so remarkable. We're making a statement about infinitely many things simultaneously. And the question we want to pursue now is simply, why? Why is this true? And you might say, well, you know, if you get out a protractor, you could actually measure the angles in any triangle. And on every triangle we've ever done this for, it's always come out to 180. That's just the way it is. Well, no, that's not the way we do mathematics. It's the way we do science, empirically. But mathematics proceeds logically. If we were working empirically just by actually measuring triangles over and over again, and we said, well, it's happened a million times, so it probably always happens, there's always the possibility that we might find some strange triangle in a cave in Syria or something like that, for which the angles did not add up to 180 degrees. That would at least be a possibility, but that's not the way mathematics works. Mathematics proceeds from logical deduction, not from empirical observation. The proof will turn out to be very simple. Oh, and by the way, sometimes students hear the word proof and they get freaked out by it, probably because of bad experiences they've had in a previous math class. Don't. All proof means is explanation. That's it. And explanations are good things. Sometimes there are beautiful proofs that convey a lot of insight, and sometimes there are uglier proofs that maybe get the job done, but don't really convey much insight. The one I'm going to show you is definitely of the beautiful type, in part because it's so simple, but it does depend on one little fact from geometry having to do with parallel lines that I'm going to remind you of. And the fact is this. If we have a couple of parallel lines, and then another line falls across them, it creates some equal angles, namely these angles. Those will always be equal in a situation like this. If you look in a basic geometry textbook, it might call these something like opposite interior angles. In my book, I just call them zigzag angles, because that's what they are. You essentially have this figure Z, where the top and bottom are parallel lines, and the zig and the zag are equal. And similarly, of course, you have another pair of zigzag angles right there. They're equal as well. So zigzag angles are equal. We could dwell on this as well if we wanted to for a while, but I have to draw the line somewhere, and this is where I'm drawing it. I'm just taking this as bedrock for this course. And we're going to use this fact to prove the thing we're really interested in, which is that in any triangle, the sum of the angles is 180 degrees. And now I'll show you why that is so. Okay, so here's the idea. We have a triangle, any old triangle. We want to show that its angles add up to 180 degrees. Well, I'm going to give these angles names. I'm going to name them by Greek letters, because we use a lot of Greek letters in trigonometry, so you might as well get used to it. And you know, one side benefit of studying this subject is that you end up learning a decent portion of the Greek alphabet. All right, so most commonly in a triangle, for the three angles, we use the first three letters in the Greek alphabet, in lowercase. And those are this guy, which is alpha, then beta. Oh, and by the way, these two letters are where we get our English word alphabet from in the first place. It's the alpha beta. And then the third letter in the Greek alphabet is gamma, which looks like that. So we're trying to show that alpha plus beta plus gamma has to be 180 degrees. Why is that? Well, here's the idea. It all comes from drawing one extra line in this picture. And this is very clever. What I will do is take a vertex of this triangle. Any one will do. I'll use this one because that's where I have the most room. So take that vertex, and the clever move I'm going to make here is to draw a line through that vertex that's parallel to the opposite side, like this. And you might say, well, why would I ever think to do that? Maybe you wouldn't think to do that, but that's okay. You're appreciating a work of art right here. If you're listening to a symphony by Beethoven, you don't stop every 2 seconds and say, oh no, I would never have thought to have put precisely those notes together in precisely that way. I'll never be able to do this. No, that's not how you enjoy a symphony. You're deeply impressed that Beethoven was able to do that. And in this case, you're impressed that someone, the first record of someone we have doing this is Euclid, about 2,300 years ago, came up with this clever idea. But still, why is it clever? You will see that in a moment. Watch. Okay, I've got my two parallel lines, but I also have this line which is falling across them, like the picture I had back here. So I have this pair of zigzag angles in there. I know that this angle is going to be equal to this angle by this basic property of parallels. So I can fill that in. That is another copy of angle alpha. Good. Hey, but wait a second. I have another pair of zigzag angles here. because I have my parallel lines, and then I have this other line falling across them. That means I've got a pair of zigzag angles right here. This angle and this angle are equal. That means this guy must be equal to gamma. And now look what we have. We were trying to figure out the sum of alpha, beta, and gamma. But now I'm staring at it because here also is alpha, beta, and gamma. And look at them. What do? They make up a straight line. And what kind of an angle is that altogether? Well, of course, that's 180 degrees, because you put two of those together and you get 360 degrees, a complete turn. So now we see that indeed alpha plus beta plus gamma, the three angles in our perfectly general triangle, is going to be 180 degrees as claimed. A beautiful little argument. And now, having seen it, in retrospect, we understand what that strange move of putting that parallel line was all about. Euclid was looking a couple of steps into the future, like a good chess player. And when we see it, we should have a little epiphany in which we recognize, 180 degrees. It makes perfect sense that the reason this holds has something to do with a straight line, because we have 180 degrees in a straight angle, just by definition. So it's not that surprising that if we're trying to show that something else adds up to 180 degrees, namely the angles in a triangle, we're going to relate them to a straight line. And that's that. It's a little logical gem. And now you know not only that the angles in any triangle add up to 180 degrees, but why the angles add up to 180 degrees. And that is the difference between real knowledge and just having some fact programmed into you. Good. So that's the first fact that we'll bear in mind about triangles, with which you were familiar already, but now, hopefully, you truly know it and understand why it is so. Let's move on to our second fact, which concerns not the angle sum of a triangle, but the area of a triangle. In any triangle, the area is half of the product of its base and its height. Now, I think pretty much anyone you stop on the street will know the angle sum of a triangle. I'm not so sure that anyone you stop on the street will know how to find the area of a triangle. But if you are in this class, you are not just anyone on the street, and you almost certainly know this famous formula. But do you know why it is true? Well, let's review it, or see it for the first time, as the case may be. The proof here is very easy indeed, and the bedrock upon which we will base the proof is something very simple, namely the formula for the area of a rectangle, which everybody knows, including that random person on the street. If we call one side of the rectangle B for base, and one of its adjacent sides H for height, then we all know that we get the area of the rectangle simply by multiplying the base and the height. So that's the very basic thing that we're going to take for granted. It's certainly permissible to ask, well, why is that true? And that could be an interesting line of thought to pursue, but we're not going to do that here. We're going to start with something that's easy to accept, and from that deduce logically that our triangle formula, which is not so obvious, must also hold. How are we going to do it? Well, as soon as I've written this down, I'm sure that some of you had an idea pop into your head. Hey, you might have thought, we're trying to show that in any triangle, the area is half the product of the base and the height, whereas in the rectangle, the area is the base and the height. Where does the half come from? And you might have thought, well, if I have a triangle like this, I can call that the base and this is the height, and then I could kind of fill in a rectangle, complete that rectangle, and then it's obvious that the area of the green triangle is half of the area of the rectangle. I mean, you can see that just by looking at this picture, and then we already know that the area of the rectangle is its base, which is B, times its height, which is H. So this would be half, because that half just comes straight down, times the area of the rectangle, which is its base times its height. So we have the area of the triangle is half the base times the height. Aha! We seem to understand it. But wait. This was a terrific insight. But this presumed that the triangle we were looking at was a right triangle. It's only with a right triangle that we can fill it out and make it into a rectangle. But this formula is supposed to hold for any triangle whatsoever. So this argument we just gave is great if we're just interested in right triangles, but we want this to be a universal statement about any old triangle. So we're going to have to go back to the drawing board. But still, this will give us some inspiration, because let's suppose that instead of a right triangle, we have a more general triangle, which is not right. The fancy term for a triangle which is not right, by the way, is an oblique triangle. If we have any old triangle whatsoever, whether it looks like that, or this, or what have you, I can't build it up into a rectangle. But what I can do is build it up into a parallelogram by drawing lines like these, which are parallel to two sides of the triangle. And I can do that with any triangle whatsoever. Like on this one, it would look like this. And so far, this is looking a lot like what we saw with the rectangle. Our original triangle is exactly half of, not a rectangle, but half of a parallelogram. So maybe if we knew something about the areas, not just of rectangles, but about parallelograms in general, we could parlay that information into a deduction about the areas of triangles. Well, that makes sense. So let's think about parallelograms for a moment. Okay, well, here's a parallelogram. Let's pick one of its sides and call that the base B. And then one thing to be very clear about, once we've picked the base, the adjacent side is not the height. The height of the parallelogram is this distance right here, the distance between whatever we're calling the base and the opposite side that it's parallel to. So that's what we mean by the height. Not that, but that. Anyway, my question is, can we say anything about the area of a parallelogram in terms of its base and height? Well, the trick, as so often, is going to be to take something we don't know about yet and reduce it to something we do know about already. We know all about rectangles. So I'm going to try to reduce my question about the area of a parallelogram to a question about the area of a rectangle. How am I going to do that? I'm going to take my parallelogram, and from this top left corner, I'm going to drop a perpendicular, thereby creating this little right triangle. And now what I want to do is to snap the triangle off and fit it into this empty space on the other side of the parallelogram, like a jigsaw puzzle. And when I do that, the result will look like this. And notice that I have neither created nor destroyed any area. I've just moved one piece around. But the overall figure still has the exact same area. So in fact, I could say that the area of the original parallelogram is the same as the area of this rectangle. But hey, that's a rectangle, and I know how to find the area of a rectangle. It's the base times the height. Obviously, the height of this rectangle is still h, and the base of this rectangle is still b, because b was the base of the original parallelogram, and all we've done is take one little piece of that base and move it over here, but it's all still there. So that means the area of this rectangle is simply the base times the height. Hey, now that's pretty interesting, and probably not known by that random person we dragged off the street. Take down all the scaffolding now that we have finished our proof, and let's just admire overall what we have established. The area of any parallelogram with base b and height h is just the product of the base and the height. Exactly the same formula that we had for the rectangle. In fact, let me rewrite it over here. Here's our parallelogram, base b, height h, and its area, we've just established, is simply the base times the height. Oh, and that immediately tells us what's going on with triangles. Because if I have any old triangle, it doesn't have to be a right triangle, it can be any kind of oblique triangle, call one side the base, and once again, remember that the height of the triangle is not the length of one of these other sides. It's this distance right here that we get when we drop a perpendicular from the opposite vertex down to the side where the base is. That's the height. Anyway, given a triangle with base b and height h, we know we could always complete that triangle, fill it out to get a parallelogram, and then we could say that the area of the triangle is, of course, half the area of the parallelogram, which is completely obvious when we look at the picture, but we know that that's going to be half of what? The area of that parallelogram. We already said the area of any parallelogram is simply its base times its height. So here that would just be b times h. And look what we have established. In any triangle whatsoever, the area of that triangle is going to be half its base times its height. And it's completely obvious now why that is so. It's because any triangle is half of a parallelogram, and the parallelogram's area is its base times its height. And so our statement, in any triangle, the area is half the product of the base times height, is something that we have established. We know why this is so. It's not just a magic formula that you were told to memorize at some point or other. You should, of course, have it in your memory, but that's not all that there should be there. You should understand where it comes from. Well, this is great. We've made a lot of progress. We now know two universal facts about all triangles. The angle sum is always 180 degrees, and we know why that is so, and the area is half the product of its base and height, and we know why that is so. By the way, before we move on, I want to dwell on this area formula for a bit, because it tells us something that might seem a little counterintuitive. When we have a formula like that, sure, it's telling us in a numerical sense, to find the area, you find the base, you find the height, you multiply them, and you cut it in half, and that's your area. Fine. But it's also telling us something very interesting. It's telling us that the area depends only on those two things, the base and the height. That means that if I have two triangles with the same base and the same height, even though they might look very, very different, I know immediately that their area must be the same. So for example, let me draw a pair of parallel lines. And here's a little line segment on the lower line. I'm going to make that the base of a triangle. So I'm going to call that B. Now, one thing this formula is telling me is that if I take any 2 points on this upper line and I connect each one to the ends of my line segment so that I get two very different looking triangles, this one and this one, the areas of these two triangles must be equal because they have literally the same base and they have the same height as well, the distance between the two parallels. And we could make this very extreme, like if we took a point all the way out here and then we had this very long triangle. It still has the same base and the same height as the other two triangles, so it must have the same area as the other two triangles. And in fact, there's only so much I can show on this screen, but you can imagine in your mind, take that point and just slide it far, far down that line, a mile down the road, a light year down the road. It doesn't matter. However far away it is, you can still join it to these two endpoints of the line segment of the base, and you'll get an extremely long, thin triangle. Well, even though two of the sides of that triangle might be a light year long, the triangle will still have the exact same area as any of these three that I've drawn here. Most people find this very counterintuitive, and yet it is so. So I think that is pretty neat. Oh, and by the way, the same kind of thing holds true for parallelograms. We proved that the area of a parallelogram is just its base times its height. So it depends on only those two things, which means if I had a parallelogram whose base was this same segment B and whose opposite side lived on this parallel line, so that we had a parallelogram like this, I could imagine sliding that top part anywhere I like on this line to get, for example, a long skinny one like this, or even a rectangle like this one, or another one leaning the opposite direction. But so long as these are actually parallelograms, tops and bottoms all have the same length, then they all have the same base, B, and they all have the same height, the distance between the parallels. So therefore, they must all have the same area as well. Interesting. And not only is this kind of thing interesting in and of itself, but I'm going to put it to use in the triangle form I just showed you a minute ago to help prove something else that you are already familiar with, even if you don't know why it holds. So let us move on. Here are two statements we have proved that hold for all triangles. Now I'm going to restrict my attention to a very special kind of triangle. There is a famous result about something that happens in any right triangle. What is this famous result? You know it, of course. It's the Pythagorean theorem. What does the Pythagorean theorem say? No, not that. Most people will say a squared plus b squared is c squared, but that doesn't mean anything until you tell me what a, b, and c are. So let's spell this out without any symbols. In any right triangle, the square on the hypotenuse, and remember, hypotenuse is just a fancy term for the longest side of a right triangle. It's the one opposite the right angle. If the right angle is here, that's the hypotenuse. Anyway, in any right triangle, the square on the hypotenuse is the sum of the squares on the other sides. The other sides of a right triangle are sometimes called the legs of the right triangle. And so this is the Pythagorean theorem. But some of you may have balked a little bit at the way I wrote it down. Not just because I didn't write a squared plus b squared is c squared, but it might have had something to do with this little word on. What do you mean the square on the hypotenuse? The sum of the squares on the other side. Don't you mean the square of the hypotenuse? It's a fair question, and I certainly could have said the square of the hypotenuse is the sum of the squares of the other sides. But when you put it that way, you immediately turn it it into algebra, where you're thinking of squaring a number, multiplying a number by itself. The Pythagorean theorem is, above all, a statement of geometry. It's a statement about triangles and literal squares. And when we think about it geometrically, some of the surprise of the theorem comes back to us. What it's telling us is that if we have any old right triangle, we have a relationship between the squares, literal squares, that are standing on the three sides of the triangle. Namely, these squares. This is the square on the hypotenuse. These are the squares on the other sides. What the Pythagorean theorem tells us is pretty remarkable. It's telling us that this square, the area of that square, is precisely the sum of these two areas. That is not at all intuitive. I've sometimes introduced the Pythagorean theorem. I actually do this very early in the book by presenting a figure like this and saying, suppose that the three squares are made of gold, and you have a choice. You can either have the one square that's sitting on the hypotenuse or these two squares right there, and you get to choose which one do you want. And if I present this on a board to students who don't really know what's coming, usually people will have pretty strong opinions about it. Maybe they want the two smaller ones because they think there's more gold altogether. Or maybe some of them think that the big one is going to have more gold. But hardly anybody, unless they're thinking about it the right way, says, well, it doesn't matter. It's the exact same amount of gold. But in fact, it is. That is what Pythagoras is telling us. And if you want to put it in terms of the familiar A, B, and C that your teacher long ago taught you, well, that's fine. C always stands for the hypotenuse in a situation like this, and A and B can do whatever you want. And then if we translated this statement into algebra, it would be telling us, well, the square on the hypotenuse, that's the area of this square, it's a C by C square, so of course it's C squared. That is going to be equal to the sum of the squares on the other sides. Well, that would be the area of this square, which is A squared, plus the area of this squared, which is B squared. So sure, that would be C squared equals A squared plus B squared if you want to write it that way. But forget that for now. The question is, why is this true, whether you state it algebraically or geometrically? There are many, many, many different proofs of the Pythagorean theorem. There is at least one entire book devoted to hundreds of different ways to prove the Pythagorean theorem. Ask any mathematician or math teacher, and they'll be sure to tell you a few of their favorite proofs of the Pythagorean theorem. In the book, I have two different proofs of the Pythagorean theorem. The first is back in chapter 4, and it's probably the cleanest proof I know of. It's very beautiful. I encourage you to go back and look at that one if you haven't read it already. And then there's another proof at the end of the current chapter. But just for fun, in this video, I'm going to show you a third proof. And the proof I will show you here is not the simplest proof by any means, but I think it's very beautiful, and it's historically interesting too, because the one I'm going to show you here is the one that appears in Euclid's Elements, which I think I mentioned earlier in this video, was from about 300 BC, and is effectively the Bible of ancient Greek geometry. Anyway, in book 1 of Euclid's Elements, there are 13 books, which can really be thought of more as chapters than separate books, but anyway, book 1 of Euclid's Elements culminates in the Pythagorean theorem. It's the 47th proposition in that book. And so I'm going to show you how Euclid did it. All right, buckle up. The goal, remember, is to show that the square on the hypotenuse is the sum of the squares on the other sides. Well, Euclid begins by drawing in a new line with a nice little bit of inspiration here. Namely, this line right here, starting at the right angle and dropping a perpendicular through the right triangle all the way to the opposite side of the square on the hypotenuse. Now, why on earth would he do that, you understandably ask? Well, this line chops the big square, the square on the hypotenuse, into two rectangles, this fairly large rectangle and this long skinny rectangle. And what Euclid is ultimately going to do is to prove that these two rectangles have the same areas as the squares on the other sides, so that when you put those two rectangles together to get the big square, the square on the hypotenuse, it's going to be equal to the squares on the other sides. So we're going to prove that this rectangle over here has the same area as this square over here, and this rectangle over here has the same area as this square. Okay, so that's the overall strategy, but how does he put it into action? Well, let's see. How he came up with this idea, God only knows. He may have learned it from someone else, or he may have come up with it himself. But either way, he began as follows. He chopped this little square in half by drawing a diagonal, and he begins just by thinking about the area of half of that square. Okay, so we've got half of this little square. It's a triangle. What do we know about the area of a triangle? Well, we were just talking about that, the area of any old triangle. It's half the product of its base and height. And in particular, we saw that any two triangles that have the same base and the same height have the same area. So he's going to take this little triangle and transform it into another triangle that has the same area. That means he needs another triangle with the same base and the same height. He's going to use this side right here as the base of the triangle. So this is its height. So we're going to take that little point right here and slide it all the way down here over into this corner. And let me draw in an extra line like that. So now I have this long, skinny triangle like this that I've temporarily shaded in blue. Notice that it has the same base, this side right here, as the original orange triangle, and it has the same height right here. So that means my new triangle has the same area as the original orange one. So I'll go ahead and fill that one in orange as well. Okay, so now I have this long, skinny triangle that has the same area as half of that original square. Now what Euclid is going to do, he's going to take that triangle and imagine rotating it, rotating the whole triangle around this vertex right here. He's going to rotate it clockwise by 90 degrees. So let's think about what happens when he rotates that triangle clockwise by 90 degrees. Well, think about this side right here. Where is it going to go? It's getting rotated by 90 degrees, so it's just going to move up here to this side of the square on the hypotenuse. Okay, that's not so hard. But then think also about what's going to happen to this side over here. It's going to rotate 90 degrees clockwise, so it's going to end up moving to this side of the small square. So after we rotate that original triangle, it's going to end up looking more like this. Do you see that? Pause the video if you don't, and make sure you can see that by following where those two sides go, because this is crucial to the argument. Anyway, once he carries out that rotation, the triangle will end up over here. This triangle that I'm outlining in blue right now. That's the rotated version of that triangle we were looking at before. We rotated it, now it's in this new position. Now the important thing is that when you rotate a triangle, of course you don't change its area. The triangle is the same triangle, you've just rotated it into a new position. So that means that the area of that triangle is the same as the area of the triangle before we rotated it, which is the same as the area of that original half of that square. So we're doing all of these moves that preserve that area, and we're going to do one more move that preserves that area. We've currently got it in this form, okay? That's a triangle. We know that the area of a triangle is half its base times its height. So if we have another triangle with the same base and the same height, we get the same area. Well, let's think of this side right here as the base, and of course, this is the height. But I'm going to take that vertex, the one that's not on the base, and I'm going to slide it down that parallel line until it hits this point right here, so that I end up with this triangle. Now, what do I know about that triangle? It had the same area as that other triangle with the same base and height, which in turn had the same area as that triangle before we rotated it, which in turn had the same area as half of that square. So what have I shown? I've shown that half of that square on one of the legs of the right triangle is equal exactly to half of that rectangle. Aha! Well, that means, of course, that the other half of that square has to be equal to the other half of that rectangle, because the two halves of the rectangle obviously have the same area, and the two halves of the square have the same area. So now we have shown, on one square at least, exactly what Euclid was trying to do. We showed that the area of one of these two rectangles that he produced is exactly the area of the square on one of the legs. And with that out of the way, now he's going to do the exact same thing for the other rectangle and the other square. I'll run through it quickly. Once again, he's going to split that other square on the other leg in half and concentrate on the area of 1/2. And now he is just going to transform that area into different triangles that all have the same area and ultimately end up with half of that rectangle. First move, keep this base right here, preserve the height, but just move that vertex down that line so that this triangle becomes this triangle. Same base, same height, therefore same area. Let me put that triangle in. There it is. A little hard to follow with all these overlapping triangles, I know. What is he going to do with that one? He's going to rotate it counterclockwise around this vertex by 90 degrees. When he does that, what's going to happen to the triangle? Well, think about two of the sides. This side, when we rotate it 90 degrees around this point, is going to become this side of the square on the hypotenuse. Meanwhile, this side, when we rotate it 90 degrees around this point, is going to become this side of that square on the leg. So when we rotate this whole triangle by 90 degrees, it's going to end up looking like this. So I will put that in orange. There it is. There is our triangle, which has the same area as the half square that we already started with. Okay, and what's the last move we're going to do with that triangle? Of course, we're going to turn it into another triangle with this same base and this same height. We're going to do that by taking this point and sliding it all the way back here so that we end up with this triangle. And so at the end of the day, we have shown that the area of this triangle, that half square, is equal to the area of this triangle, that half rectangle. And because that half rectangle is equal to this half rectangle and this half square is equal to this half square, that means that those corresponding parts must be equal too. And so what have we shown? You know, I really probably should have put those second orange things in a different color. That's better. That way the red things are equal, the orange things are equal, the green things are equal, and the blue things are equal. But anyway, we have shown that you can rearrange the area in the square on the hypotenuse in such a way that it fills out the squares on the other sides exactly, right? Or vice versa. And we have therefore proved the Pythagorean theorem. A beautiful proof. I hope you understood it and could appreciate it. If you had trouble with that proof, as I said, it's not necessarily the easiest proof to follow, though it's not that bad if you concentrate. There are many, many other proofs out there. Everyone should know at least one proof of the Pythagorean theorem, just to be a reasonably cultured human being. Well, if you have followed all this, then congratulations. You now understand proofs of 3 basic statements about triangles. I do want to add a few pragmatic computational thoughts about the Pythagorean theorem. First of all, one thing the Pythagorean theorem tells us, another way to think about it, is that if we have any right triangle, the Pythagorean theorem tells us that as soon as we know any 2 of the sides of that triangle, that right triangle, we automatically know the third one. We have this relationship between the 3 sides, or rather the squares of the sides, or the squares on the sides, however you want to think about it. It's a relationship between 3 things that has to happen. So if we know any 2 pieces of the puzzle, we get the third one for free. For example, if I have a right triangle whose hypotenuse is 13 and one of the legs is 12, but I don't know the other leg, I should be able to figure it out using the Pythagorean theorem, because the Pythagorean theorem relates precisely those 3 things, the 3 sides of any right triangle. Or if I have a right triangle whose legs are 2 and 5, but whose hypotenuse is unknown, well, the Pythagorean theorem will tell me what the hypotenuse is, because the Pythagorean theorem is a relationship between the 3 sides of any right triangle. Now, let me show you, or let me remind you, how you would come up with these missing sides the first time you ever met the Pythagorean theorem, back in an algebra course or something like that. And then I want to show you a quicker way to do it in your head, which is what you'll probably want to use moving on. So let's start with this lower one. How did you do that back in the old days? How did your teacher teach you to do it? Probably something like this. He or she probably told you not to put something undignified like a question mark, but to call that c, because it's the hypotenuse. And then you'd write down an equation, right? You'd say c squared is 2 squared plus 5 squared, which is 4 plus 25, which is 29. So therefore c must be the square root of 29. And of course, that's correct. There's nothing wrong with that at all. And similarly, for this first one, you would have said, oh, don't write a question mark, give it a name, call it a. And then you'd have, what does a Pythagoras tell us? 13 squared, because 13 is the hypotenuse, is going to be a squared plus 12 squared. And then you'd shuffle these guys around a little bit, solve for a. You'd say, well, that's 169 is a squared plus 144. Subtract that off, and we'd get a squared is, what is that? 25. So a must be 5. And again, nothing wrong with that. It gets you what you are looking for. But it's a pain. You have to introduce a new symbol, like A here and C here, and you have to write all this junk down. There's a much, much quicker way to do it in your head. And by the time you're in a class like this, where we'll be using the Pythagorean theorem a lot, you want to be able to do it in your head and move on. And if you're still writing stuff like this down by the time you get to calculus, it's going to start to look a little embarrassing, frankly. So now's the time to learn how to do it quickly. So I'm going to show you that. First, let's consider the case where you know the 2 legs, but you don't know the hypotenuse. Well, if you did this the way your teacher taught you, and again, he or she taught you right, because this is how you should do it the first time, you'd write down an equation corresponding to the Pythagorean theorem, then you're solving for c, so you take square roots of both sides to isolate c, and you'd end up with this expression. C is the square root of a squared plus b squared. And that's more or less what we want to remember. But I'm going to express it rhetorically rather than in symbols. So I'll call this the PT shortcut 1, Pythagorean theorem shortcut 1. If the legs are a and b, I guess I'm using a few symbols, the hypotenuse is the square root of the sum of their squares. And that's exactly what we showed right here. We're just going to remember it in this form. So let me move this up. So for example, if we have a right triangle whose legs are 2 and 7, what's the hypotenuse? Without calling it c and writing c squared is 2 squared plus 7 squared. What is it in one shot? We just want to write it down right away. It's the square root of the sum of their squares. So it's the square root of 4 plus 49, which is better known as the square root of 53. And that's it. And if you're doing this on a test or something like that, and you're worried about showing your work, just say, by the Pythagorean theorem. And that's it. Your teacher will understand completely and be happy that you haven't cluttered the page with lots of unnecessary symbols. Let's do one or two more. Let's say you have a right triangle whose legs are 5 and 6. What's the hypotenuse? Well, it's the square root of the sum of their squares. That's 36 plus 25. That's what? 61. So the hypotenuse is the square root of 61 by the Pythagorean theorem. Easy, right? Here's a right triangle whose legs are 10 and 3. What's the hypotenuse? Well, by our shortcut formula, it's the square root of the sum of their squares. So in other words, 100 plus 9. It is the square root of 109 by the Pythagorean theorem. Piece of cake, and it will save you a lot of work in this course and courses to come, because I promise you, when you're taking calculus or physics or whatever, that is exactly what your teacher is going to do. He or she is not going to slow down and say, well, we'll call this one c, and then we have c squared is 9, but it's just not going to happen. So if you understand this, you'll be able to follow what's going on without saying, wait, where did that come from? But understand where this shortcut came from. It just came from applying the Pythagorean theorem the way you learned it in an algebra class in the past. And where did that come from? Well, we have now seen a proof of the Pythagorean theorem. That's where all the intellectual action is. Oh, but this was Pythagorean shortcut 1. I need to show you Pythagorean shortcut 2. The second shortcut is not about when we know the legs. This is about if we know the hypotenuse. If the hypotenuse is c, and we know one leg is, let's just call it L, then the other leg is, well, what's it going to be? Let's reason it out. I'm going to have to get rid of my beautiful drawing. Alas. Okay, so we're going to derive this shortcut formula. We know the hypotenuse is c, and we know one of the legs is L. So who's this other fella? We'll give him a name. Call it whatever you want. Is it A? Is it B? It doesn't matter. Call it smiley face for all I care. Don't do this in your class. But for the purpose of this video, we'll call it smiley face for a second. What is this telling us? Or rather, what is Pythagoras telling us about this situation? From this, we know c squared, the square on the hypotenuse, is what? L squared plus smiley face squared. Like so. But we're trying to solve for the smiley face. I wish I had used another symbol now. So what do we have to do? We have to subtract L squared off both sides, which gives us c squared minus L squared is our unknown thing squared. And then we're going to take square roots of both sides to solve for our unknown side. And we see that our unknown leg turns out to be c squared minus L squared under a square root. So that's what we're looking for. We don't have to reinvent the wheel every time we have to solve a problem like this, because we will end up solving things like that frequently. We're just going to remember that if the hypotenuse is c, like it is here, and one leg is L, like it is here, the other leg, this guy, is going to be the square root of, now it's not a sum of the known sides, but a difference of the known sides. You have to remember which order they come in, of course. It's the hypotenuse squared minus the other leg squared. But since the hypotenuse is the longest one, it wouldn't even make sense to turn it around. You'd have the square root of a negative. But anyway, that's it. That's our second Pythagorean shortcut. And I suppose we should do an example or two just to show you how it works. So here's an example. Let's say we have a right triangle, and we know that the hypotenuse is 9 and one of the legs is 7. What's the length of the other leg? Well, we know that the Pythagorean theorem will do the job, because if you know any two sides of a right triangle, the Pythagorean theorem gives you the third one. In this case, we know the hypotenuse, so we're going to end up with a square root of a difference of the squares of the other sides. So that's going to be 81 minus 49. Well, 81 minus 50 would be 31, so take away only 39, and it's going to leave you with 32. And that's that. How did we get that? By the Pythagorean theorem. Easy, is it not? Here's another one. Let's say we have a right triangle where the hypotenuse is 7 and one leg is 1. What's the other leg? Well, it's a right triangle. We know two sides, so the Pythagorean theorem will give us the third. It's always going to be the square root of a sum or difference of squares. It's a difference in this case because we know the hypotenuse. So it's going to be 49 minus 1. So square root of 48. One more. Here's a right triangle. Here are two sides, 4 and 6. What's the remaining side? Well, it's a right triangle with two sides. Pythagorean theorem will give us the third. We know it's going to be the square root of, well, in this case, it's going to be a sum of squares of the other sides because we know the two legs. So it's going to be the sum of 36 and 16, which is 52. In that one, we used the first Pythagorean shortcut. I did that just to keep you on your toes. I said that was going to be the last, but we'll do one more. Okay, here's a right triangle. Hypotenuse 3. This leg has length square root of 2. What's the remaining leg? Well, we know we can get it with the Pythagorean theorem. We're going to end up with the square root of either a sum or difference of squares. It's a difference in this case because we know the hypotenuse. So it's going to be 9 minus the square of this side, which is 2. So square root of 7 is the remaining side. And that's that. So keep these in your head. It is important to have things in your head. When I talk about the importance of understanding things, I don't mean at the expense of memory. You should remember things as well, but you also want to understand where they came from. Otherwise, it's just a bunch of memorized gibberish. You should be able to stop at any time. If somebody asks you, wait, why does that work? You should be able to explain to somebody why it works. All right, I was originally intending to go a little further in this video, but I think I'm going to end up spreading it over 2 videos so that it does not become too long. So I will be back next time to talk about congruence and similarity of triangles and how much information you need to determine a triangle. And that will be that for Chapter 8. So until next time, goodbye.